based on our previous work, we've seen that things happen, local maxes and mins specifically, happen when we have a derivative equals 0 or potentially derivative does not exist. For that reason, those values are given the name of critical numbers. So by a critical number, all we mean by a critical number is for function f, c, number c, is a critical number, a critical value. Sometimes you'll see that word as well. If f prime of c equals 0, or if f prime of c does not exist. So it's two things. When you're finding the critical numbers for a function, you're finding two things. Sometimes it may be just one of them, but potentially it could be both of these things to be a critical number. And so that's our next step here is let's find some critical numbers, all right? So let's find the critical numbers for f of x equals 3x to the 4th minus 16x cubed plus 18x squared. So the critical numbers are where the derivative equals 0, the derivative does not exist. So obviously when you're finding the critical numbers, the first step will be to find the derivative, if you can, specify it. So that would be 12x cubed minus 48x squared plus 36x. Do that right? So in the critical numbers, we're thinking about two possible we're either going to do the derivative equals 0, derivative does not exist. All right, so find your derivative, set it equal to 0, will be the first piece of this. Well, all right, so solve that, a little bit of factoring. 12x is a common factor, so factor off of 12x. That'll give us x squared minus 4x plus 3. And then that factors on down to x minus 3, x minus 1. And so that would be, set each of those to 0, 3 different values. This would be 0. This would be add 3, x is 3, add 1, x is 1. And like I said, we need to consider it, but you won't always have both things, both parts of the critical numbers involved here, because is there anywhere derivatives not exist for that? No. What you're looking for, mainly what we'll be looking for there on the derivatives not exist is denominator equals 0. That would be mainly, I mean, it could be derivatives not, sometimes you have a corner, like an absolute value corner, but I don't even think we have, on this assignment anyway, we don't have any of those. So mainly what you're looking for here, so you're looking for corners, but denominator equals 0 is for f prime. Corners, discontinuities, which that's other discontinuities, I guess I should say. That's the main thing you're looking for, denominator equals 0. And of course here, in the derivative, we don't have any denominator equals 0s. This one doesn't have any corners, other discontinuities. So f prime does not exist here. There's no no critical values here. So sometimes that'll happen. One or the other may have something and not the other one. All right. So anyway, those are it. Those are the three. Okay. Now I did this one specifically because do you recognize that one? That was the first one we did on the handout. This is the function number 1 on the handout. And what did we find at x is 0, x is 3, and x is 1? What were these at these locations for x values? What were those? Were those the local mins and maxes? Yeah. At f of 0, f of 3, and f of 1, we either had a local min or a local max, okay? Yeah, so this, again, this just confirms that what we're finding here, these critical values, are potential local maxes or mins. That's the whole idea in doing this, okay? And we'll use that fact in other places, but that's what I wanted you to recognize also. These are where the local mins and maxes will occur, these critical numbers. And that just confirms it from number 1 on the handout there. Okay. All right. How about critical numbers for this one? F of x equals x to the 4th minus x squared. All right, well, critical numbers need the derivative, so that would be 4x cubed minus 2x. Set that equal to 0. 4x cubed minus 2x equals 0. So that's 2x. Common factor, so that would put us at 2x squared minus 1. In the parentheses there, if we factor off the 2x. So we've got 2x equals 0, 2x squared minus 1 equals 0. Well, that's of course x is 0. Over here we've got 2x squared equals 1 divided by 2. So x squared is a half, so that would give us, solution-wise, plus or minus a half, which is, just to approximate that, what is plus or minus square root of a half? It's about 0.707, yeah. About 0.7, plus or minus. Well, the reason I do this one too, any does not exist. Well, again, since it's just a simple polynomial, there's not going to be anywhere over that derivative. There's no x value that doesn't exist there. So there's no critical numbers there. But yeah, so we do have 3 though. Now, if you look at the graph of this one, guess what we'll find with those critical numbers? Guess what we find on the graph of those, at those values? See, x to the 4th minus, x to the 4th minus x squared. May have to zoom in a little bit, right? Yeah, so I've zoomed in 1, 2, pretty tight. Crosses at 1, bounces just a little bit there. Okay, there's your graph. What have I got at 0 and plus or minus square root of a half for x? Well, I've got a little peak there, don't I? It's not a real big peak, but it's a peak. I got a peak at 0, don't I? And then plus or minus 0.7, guess where those are? Yeah. This is, well, to be specific, it would be the negative square root of a half right there. And this would be, at the valley anyway, square root of a half right there. Okay? So that's where our peaks and valleys are hitting. Now, reason I mention that is because, would you guess that that valley is square root, a negative square root of a half? You probably couldn't come up with that. And that's a positive square root of a half. So this gives us a way to hone in on, find the exactness, get the exact value where, I mean, we could probably estimate, well, it looks like it's about 0.7 or negative 0.7, but it's exactly negative square root of a half and positive square root of a half. Okay? So this gives us a way to find it specifically. All right? Now, one thing I would point out also here, well, let's do this one. F of x equals x to the 3/5 minus x to the 1/5. Find the critical numbers. All right, so f prime here is 3/5 x to the subtract 1, you got negative 2/5, right? Minus 1/5 x subtract 1, you got negative 4/5. For my derivative. Now, if you get those negative exponents, especially on these critical number problems, my recommendation, make those positive exponents by flipping them over. So let's change this to be, it would be 3 over 5 x to the 2/5 minus 1 over 5 x to the 4/5. Change it to that form. Make it a positive exponent in the denominator. Flip it over before we do our calculations here. Find those critical numbers, okay? Now, so the critical numbers here, all right, so we've got to do f prime of x equals 0. So we're going to set that in that form equal to 0. This is one of the reasons for doing that, because it makes this solving, we probably haven't solved a whole lot of those types of equations. So this is sort of a new foray into a new territory here, but it's not that bad, okay? Let me show you how, one way to do this is, think about the least common denominator here, which, again, probably haven't tackled a whole lot of these where you have a fractional exponent. But the least common denominator would be 5, and then I've got x to the 2/5 and x to the 4/5, so the least common multiple of those, well, x to the 4/5 is larger, so that's one we're going to go with. So 5x to the 4/5 is my least common denominator there, and what I'm going to do is multiply that on both sides. I'm going to multiply that by everything. 5x to the 4/5 by everything. So 5x to the 4/5 times the 3 over 5x to the 2/5, 5x to the 4/5 times 1 over 5x to the 4/5, and then 0, 5x to the 4/5 times 0. And a couple of those are easy, and however, we start with the harder one here. All right, so we're multiplying each by that. Well, like I said, basically started with the harder one here, but it's not that bad. The 5's cancel. What happens to this x to the 4/5, and then you've got a x to the 2/5 on the denominator there? Well, it's a little subtraction, isn't it? When I have x to the 4/5 divided by x to the 2/5, I subtract those exponents. Like if I have x to the fifth times 1 over x squared. That's dividing, so I subtract the exponents, the x cubed. It's subtraction. It's just subtraction. So what do I get? I get 3, and then it's x. So I get 4/5 minus 2/5. Well, that's 2/5, isn't it? X to the 4/5 simplified, divided by x to the 2/5 is x to the 2/5. Because you're subtracting those exponents. Okay? Like I said, that's the hardest one of these. Because what happens here? They both cancel out. So that's just minus 1. And then, of course, 0, that's also easy, times x to the 4/5. 0. Yeah, so that takes that equation to this equation, which now, let's do this. Let's add the 1. Let's get x to the 2/5 by itself. So let's add the 1. So we got 3x to the 2/5 equals 1. Divide by 3. And so we'll have x to the 2/5 equals 1/3. So now we're getting somewhere. What does this 5 mean? As far as, it's a root, isn't it? If you have a denominator power, that's a root. So this is the 5th root involved here. It's 5th root of x squared, but if I'm doing a root, like a square root, or equals 5, or a cube root of x equals 7, what do? In this case, I square both sides. In this case, I cube both sides. Well, this is 5th root. So guess what I'm going to do? 5th power both sides. So raise both sides to the 5th power, and that'll cancel that 5 out. So I'll have x squared equals 1 to the 5th is 1, and 3 to the 5th. What is 3 to the 5th? 243? Yes? 1 to the 5th is 1, and 3 to the 5th is 243. Okay? So I've got x squared equals 1 over 243. Well, now it's just an x squared equation, so I'm going to square root both sides. But what can this side be? Plus or minus? Yeah. So that's a little, quite the process there. Any question? So plus or minus the square root of 1 over 243. However, we're not done. Finding the critical numbers. On the critical numbers, you got to look at two things. So far, we haven't come up with anything where the derivative does not exist, but this is another reason for putting it in this form. Here's my derivative, right? And I said, what you want to look for on the does not exist, mainly the ones we are looking for is where the denominator of the derivative does not equal 0. That's look for where denominator of f prime equals 0. So over here I've got two denominators. What would make either one of those be 0? It's 0, right? In that either case, 5x to the 2/5 equals 0. That's if x equals 0. And the same thing for 4/5. 5x to the 4/5 equals 0. Well, it's x equals 0. I mean, you can go through the process and do basically the same thing here, but hopefully, clearly, it's 0. So that is another critical number here. It's what I'm getting at. 0 is another critical numbers beside. So sometimes you do get something from that does not exist. Okay? All right. Yeah, I probably couldn't really tell much about the graph on that one. So what I was going to show you though, all right, so what we would expect then is that 0 and this plus or minus, that would be where, look for those maxes and mins, right? But let me show you this. Just because we get a critical number doesn't mean we get a local maximum. Here's a good example of that. F of x is a very simple one. F of x equals x cubed. What are the critical numbers there? Well, there's just one, but set the derivative equal to 0, does not exist. Derivative is 3x squared. So my derivative equals 0, would be 3x squared equals 0. We can go through the whole thing, but it's where x squared equals 0, that's x is 0. And that one doesn't have any denominators or anything special going on, so does not exist. There's not any. So we do have a critical number at x equals 0. But does the local min or max exist at x equals 0? What does this graph look like? So my question is there a local min or max at 0? What does this graph look like? You know what that looks like, right? It says, it's just a little line with a little kink in it there, you might call it. But is there a local min or max at 0? There's not a local min or max at 0 there. So what I'm saying is, yeah, we're expecting probably, there's going to be local mins and maxes at these values, but it doesn't always have to be. Okay, just because you've got a critical number, that doesn't guarantee that you have a local min or max, is what I'm saying. Okay, so it's not always, yeah, that's guaranteed to be a local min or max. No, this is just a good place to look. It may not be a max or a min, but it's a good place to look. If there is going to be a local min or max, it is going to be at a critical number, but not all critical numbers give you local mins and maxes. There's a difference. Okay? Question, thought on